So you probably heard about fusion. So fusion is the process that powers the sun. Here on Earth, we try to recreate that, even though in order to do this, we really have to heat up gas in very, very high temperatures, much higher than actually the core of the sun. So the way that fusion works is that we need gas, we need to heat it up to million degrees Celsius. Now, when gas is heated up in such conditions, there's really no neutral atoms or molecules, but it's more of a soup of charged particles. So this is plasma. We need plasma to make fusion work here on Earth. And the full point about it is that we need to being able to make the plasma, heat it up, stabilize, confine it, and control it. And this is really the art of doing plasma science. So TAE approach is this very unique type of plasma configuration called field reverse configuration, or FRC. So what really is, it's about the shape of the plasma. So other devices like tokamaks, they have like a donut shaped plasma. In our device, the FRC is more of a smoke ring that is spinning. And as it spins, it creates its own magnetic field and then it self-organizes. Similarly to a tornado that kind of self-organizes out of thin air. So you can imagine that to get this special type of plasma, the FRC, you need very special conditions the same way as a tornado does. The reason TAE chose FRCs and the reason we really like them is because they're high beta. Now, this is a metric of plasma performance, but what it really means is that we can have very high plasma pressure with less magnets. So that makes the whole thing simpler, more compact, but also at the same time, it's very well suited for advanced fuels like PB11, so proton 11, which is the type of fuel that TAE wants to use for the fusion power plant. So I'm super delighted to introduce to all of you our new machine configuration called Norm. So Norm came from Norman. So Norman was TA's fifth device, and it was the flagship. Most of you knew Norman or C2W. So Norman became Norm because it's much, much shorter, and it's actually a big breakthrough machine and TA's latest breakthrough device. So Norm is the first device that can produce the special shape of plasma we just discussed, the field reversal, just by using neutral beam injections. So this is super exciting because scientists all the way back to the 70s, they would try to figure out different ways to produce FRCs using particle accelerators, but they haven't succeeded until now. So what are the differences between Norman and Norm? So historically, in order to make FRCs for fusion, you would need to have theta pinch coils, so special type of coils at the both ends of the machine. So let's say south and north. The plasma we produce, it will get accelerated to supersonic speeds. Then we will use our neutral beam injectors to add more current and stabilize. But Norm does not require that. We are able to create the field reversal, but then also maintaining just using the neutral beams. So it's really a huge simplification of the hardware compared to Norman. And you can actually see here that we used to have a formation section for Norman. It was a very long quartz tube. The coils, all it's missing. Now Norm is significantly more compact. And actually what you see here is one of the old diverters, which is a part of the machine. We don't need this anymore. It's disconnected. Going from Norman to Norm simplified hardware a lot. So almost like 50% of all this hardware is missing. But I think the beauty of it is in the scientific breakthrough. And then the fact that in the end, when you think about fusion plasmas, it's about temperature, it's about density, and it's good to focus all the efforts on trying to maintain this like very steady state hot plasmas. Norm, just with neutral beam injection, with no formation section, no complicated coils, actually produce our top performing steady state plasma. So that's really great. What you may notice is that there was a huge of machinery here, the quartz tubes of the formation section and the second diverter. now all this machinery with norm is gone. So it's actually amazing how Norman would get reconfigured to norm, and then we continue to experiment with norm every day.
Hello, everyone. My name is Brendan, one of the scientists here at TAE, and I'm standing at one end of Norm's sausage-shaped confinement vessel, where behind some of these diagnostics and cables, you might be able to see some of these red ring-shaped cases. These red steel cases contain Norm's electromagnetic coils. So just like other magnetic confinement devices, Norm uses a magnetic field to confine its superhot plasma and keep it away from the walls. There are 8 of these large magnets going down the length of the cylindrical confinement vessel. Unlike some other fusion devices you may have seen, you might notice that Norm's external magnet coils are simple, planar rings spaced along the confinement vessel, like a giant solenoid. This makes the engineering of TAE's reactors much simpler than that of the donut-shaped reactors like tokamaks and stellarators. Furthermore, our FRC plasma is simple and stable enough to achieve what we call high beta, which basically means that a tokamak would need 10 times stronger magnets to contain the same plasma pressure that Norm does. This high beta, or high relative pressure of the plasma, is one of the unique characteristics of TAE's configuration that enables the path to advanced fusion fuel cycles beyond deuterium and tritium. The ultimate goal of our company is to use PV11, which is e-neutronic, and therefore much more friendly to use from a materials and regulatory standpoint. One consequence of our high beta linear confinement system is that we have open magnetic field lines that carry our plasma leakage out the ends of the confinement vessel. So here, at each end of the confinement vessel, we use a couple of stronger magnets to pinch the magnetic field down through this smaller vessel. We can pinch it even stronger now that we don't need to shoot plasma through it from the formation sections. That pinching of the field reflects a lot of the leaky plasma back into the confinement vessel, and because it reflects plasma like that, the effect is known as a magnetic mirror. The little bit of real leakage passes through the mirror and comes out the other end, and that's like the exhaust of our fusion reactors. So here's where we have another advantage over the donut-shaped machines. Since our exhaust comes out the ends, we have unlimited space to expand it and cool it off before it hits metal. That happens in this arbitrarily big vessel here, which we call a diverter. Let's get another look at it from down behind. As Greta mentioned earlier, the diverters also contain several high-voltage electrodes that we use to control the rotation of the plasma. Here at the back of the north diverter, you can see all the high-voltage feed-throughs that carry the power and instrumentation signals to the many electrodes, as well as another big red magnet coil. Actually, someday we may be able to use the electrodes like these not only to control and heat the plasma, but also to directly convert the plasma exhaust to electricity, bypassing the inefficiencies of a steam cycle. And with no formation sections anymore, we've now reached the north end of the machine. So let's go back to the center of the machine, where James will tell you more about the neutral beam system that creates and sustains our main FRC plasma.
We're standing outside one of our 8 neutral beam systems. The neutral beam system is composed of 2 main components: the ion source, which is this yellow can, and the neutralization chamber, which is this silver larger can. Inside the ion source, there are 4 arc plasma generators that provide a plasma for which the ions that make up the neutral beam come from. At the end of that plasma chamber, there are metallic grids with electric potentials that not only extract those ions from the plasma and accelerate those ions, but they also suppress any electrons that are created within that grid system. After the ion beam is formed, it travels into the neutralization tank where there's a gas chamber. Those ions interact with the slow-moving gas, stripping away electrons from that gas, neutralizing the ions. And this process is very efficient. Most of the ions are converted into neutrals. That continues to travel through a vacuum duct into the confinement vessel and into the center of the field reverse configuration plasma. The process of creating a field reverse configuration via neutral beam injection starts with an initial seed plasma. Plasma is created by plasma generators on either end of the device with biased electrodes and magnetic field coils along the axis of the machine, all here in red. The 8 neutral beam systems then provide the neutral particles that interact with that seed plasma. As they are ionized and create fast ions, they encircle that seed plasma. The confinement allows the fast ion population to increase. As that fast ion population increases, the current generates a magnetic field. The superposition of that generated magnetic field from fast ions and the generated field by the coils creates a closed field line system. Thus, you've created a field reverse configuration plasma. Neutral beam injection is one of the most essential tools in magnetic confinement fusion. It works by launching beams of fast neutral particles directly into the center of the plasma. These particles bring both energy and fuel into the plasma, helping sustain the plasma by heating and feeding it. We use neutral particles because they aren't affected by magnetic fields like charged particles are. This means they can travel past the outer, more lossy regions of the plasma and deposit their energy right to where it's needed most, in the dense core where the magnetic field lines are closed and the confinement is strongest. In a beam-driven reverse configuration plasma, neutral beam injection takes on an even more critical role. Initially, neutral beam fast ions were used in a field reverse configuration plasma to stabilize the plasma. The increased velocity of the particles have larger orbits compared to the thermal particles, and so their orbits can average over all the small perturbations and turbulence, which stabilizes the MHD activity. Now the population of neutral beam fast ions is so large, it actually reverses the magnetic field, which is key to forming one of these types of plasmas. Norman, the first iteration of C2W, created 2 closed magnetic field line plasmas at either ends of the device and accelerated them towards each other. They would form a much larger FRC plasma in the middle. Now we simply create the closed field line plasmas with the neutral beam injection, significantly reducing the complexity of our reactor.
Hi there, I'm Jeff Weinkoop, one of the engineers here at TAE. Our engineering team here has a very diverse workload. One of the most important tasks we do is design the machine layout. Obviously, this includes the complicated design of the confinement vessel, but we also need to ensure that every part of the facility is able to support the incredible research we do here. This includes electrical grounding, such as these copper pads that run the entire length of the machine. It also includes designing in service access and machine cooling for all of the equipment you see around me. On a daily basis, the engineers work closely with the physicists to develop diagnostics that help us better understand the plasma behavior. Things like its temperature, its density, and its rotational velocity. These diagnostics include interferometers, which use lasers to measure plasma density by detecting tiny shifts in light caused by electrons losing energy. Spectrometers, which tell us about plasma temperature, ion species, and impurities present in the gas by analyzing the wavelengths and the Doppler shifts in the light coming off the plasma. Additionally, this whole machine is covered in tons, hundreds of magnetic probes, flux loops, and Rogowski coils. All these help us better understand the shape of our plasma and the FRC that we generate. Lastly, we also have fast imaging cameras throughout the machine, which allow us to capture how the plasma shape evolves over time, and also how the plasma interacts with the vessel walls. Speaking of the vessel, which you can see right here behind me, it's about 6.5 meters long in overall length and 1.5 meters in diameter. Overall, the volume of it is about 12 cubic meters. The most important thing about this vessel is its vacuum level. Between shots, we bring the vacuum inside this vessel down to about 10 to the -9th torr. That's 1 trillion times lower than the atmospheric pressure here at Earth. At that level, the mean free path, which is the distance a particle can travel before colliding with another gas particle, is about 53 kilometers. That's an insanely deep vacuum right there. That's equivalent to the vacuum level between Earth and the Moon. The vacuum levels we achieve here at TAE are comparable to a semiconductor manufacturing facility, but we don't have the clean room conditions here, though our system is built to withstand far more rugged environments. We use several major pumping systems, especially around these diverters over here. These pumps are powerful enough to move the equivalent of 2 million liters of air per second if they were able to operate at atmospheric pressure. That's fast enough to evacuate the entire machine hull area in about a second. So why do we need such a huge vacuum? Because it ensures the machinery is virtually empty before we inject our working gas. That way we know the plasma only contains the particles we want and nothing that we don't. When plasma energetic particles hit the vessel wall, they can knock loose trapped molecules like water, oxygen, and nitrogen. These impurities can cool the plasma instantly, which is something we do not want to have happen. Even though the vessel walls look polished, on a microscopic level, they're full of tiny scratches, which, relative to the atoms, about the size of a Grand Canyon, even though they look fine to the naked eye. These small cracks and crevices are where these imperfections or these impurities can hide. In order to fight this, we use a combination of turbopumps, cryopumps, and most importantly, a technique called gettering. In gettering, we spray coat the interior walls of the vessel with a thin film of titanium. Titanium is a reactive light metal that has high chemical affinity for these stray atoms. When they touch the titanium, they form a strong bond, so these particles get chemically bonded to the titanium and trapped to the vessel walls. This prevents them from re-entering the vacuum space and cooling down our plasma. This all helps us keep the vacuum clean, the plasma hot, and the fusion process on track.
Hi, I'm Eli Park, one of the diagnostics scientists here at TAE Technologies. Our group has deployed more than 70 diagnostics across NORM to measure a variety of plasma parameters like temperature, density, velocity, and electric and magnetic fields. We're here inside the laser hut, where we keep one of our primary laser diagnostics, the Thomson scattering system. The lasers in this system operate in the near infrared at about 1 micron to measure electron temperatures and densities inside our plasma. These two laser systems produce a large number of photons, most of which pass through the plasma without really interacting with it. But a very, very tiny fraction of those photons will scatter off of the electrons in the plasma, and we can measure those scattered electrons with very sensitive detectors, which are in a separate room. Based on the electron velocity, those photons will shift slightly in wavelength, and we can measure that wavelength shift and the overall broadening in the spectrum to determine the plasma temperature. And the strength of the spectrum will give us the plasma density. These two systems, the system right here in front of me, is a commercial off-the-shelf Nd:YAG laser, which operates at about 100 hertz and makes measurements in the mirror region of our plasma, whereas the other laser here is a custom-built high repetition rate using diode pumped lasers and can operate at typically kilohertz repetition rate frequencies, but also can operate up to 25 kilohertz, which is quite fast for a Thomson scattering system. And so we can use these lasers to make measurements in a wide variety of plasma conditions, and the ability to make very rapid, high time resolution measurements up to 25 kilohertz means that we can make quick changes to our plasma, like changes in the neutral beams or the electrodes, and we can precisely target our measurements to get high time resolution of dynamic behavior exactly when we want it. So here you can see some of the optics that deliver our far infrared interferometry beam to the plasma, with the beam split out into 14 chords across the width of the device. The structure that they're mounted on is approximately 30 tons, and it's designed to minimize the impact of vibrations to improve the quality of our measurements. You can also see some of our insertable probes like this one here, which we use to make measurements of density and potential in the edge of the plasma. And this large object behind me is one of our neutral particle analyzers. We use these to measure the energy and mass of particles leaving our plasma, and we can use that to infer behavior that's happening inside the machine. We also have more than 600 magnetic probes spread out across the machine to measure the magnetic field and flux through our device. And we have a variety of spectroscopic measurements. These spectroscopic measurements use either spectrometers or fast cameras with filters. The fast cameras can make measurements up to 50,000 frames per second. And we use these spectroscopic measurements to look at line emission from hydrogen or deuterium or impurities like oxygen. And looking at the line emission from these ions in the plasma, we can make measurements of the ion temperature as well as the velocity. So for example, when we're firing our neutral beams, and they're driving rotation in the ion direction. And we're also using our electrodes at the end of the machine, which create an electric field in the center of the machine and drives rotation in the electron direction. So we can measure the balance between the forces from the electrodes and the beams and look at the rotation and the shear of the velocity profile in our plasmas. Another important laser diagnostic that we use is our far infrared laser interferometer, which you can see here. This system operates in between the infrared and the microwave in a range of frequencies that are also known as the terahertz. Our lasers are entirely designed and built in-house using commercially available CO2 lasers to pump formic acid vapor. The CO2 lasers operate at about 10 microns, and the formic acid vapor converts this light into 432 micron wavelength radiation. We use it in 2 different lasers, which are tuned slightly differently to create a beat frequency of about a few megahertz between them. So the plasma index of refraction depends on the density of the electrons. And so when we pass one of these laser beams through the plasma, it'll pick up a slightly different phase shift compared to the laser beam that doesn't pass through the plasma. And then when we measure the beat frequency due to interference from these 2 beams on our detectors, we can use changes in that beat frequency to measure changes in the electron density in the plasma. We make measurements on 14 different paths through the plasma, which lets us measure the plasma density profiles. We can infer position and shape of the plasma, and we can also measure fluctuations due to a variety of phenomena in the plasma, including from energetic particles or MHD activity inside our plasma.
Hi, I'm Katya Chekwitz, one of the controls engineers here at TAE. Flanking me on either side are just a few of the many cabinets that comprise the power supply systems that support our fusion experiments. Over 100 of these cabinets populate our machine hall, delivering power to our neutral beams, biasing system, plasma guns, and various other high-power systems. Since the power feed we get from the grid is only about a megawatt, we must charge these supplies over the course of several minutes in order to reach the energy levels necessary for a plasma shot. When fully charged, some of these systems can achieve current on the order of 100,000 amps, at potentials in the tens of thousands of volts. To put that in perspective, most cell phone chargers charge at approximately 5 to 12 volts and only put out about 1 or 2 amps of current. The distinguished expertise that we have developed in energy storage and delivery forms the basis of our Power Solutions subsidiary, which is adapting these systems to use in EVs, homes, and businesses. As one might expect, discharging such vast amounts of energy in just fractions of a second generates significant heat. Despite the massive thermal loads, we managed to keep these power supplies cool to just 60 degrees Celsius, or about 140 degrees Fahrenheit. Our on-site cooling system chills and delivers water on demand to these systems as well as the neutral beams, diagnostic lasers, and other systems that need it. A programmable logic controller, or PLC, orchestrates the many pumps, valves, and sensors needed to achieve adequate cooling of our machine. This PLC also monitors for leaks and alerts us to any issues that may arise. A second PLC manages a combination of convection and hot cathode ion gauges, which determine the pressure within our many vacuum vessels. This PLC also controls a system of roughing, backing, and turbomolecular pumps, which are used to maintain ultra-high vacuum. Each turbo pump has a pumping rate of about a cubic meter per second. These pumps can pull enough air out of our machine to create an environment that is 1 trillion times lower in pressure than that of our atmosphere. That's about the same pressure as in outer space between the Earth and our moon. A third PLC monitors the status of each power supply system, opening and closing safety contactors or switches as needed to protect the system and our personnel. These PLCs work in tandem with our machine control system, which takes advantage of highly specialized equipment that can track key metrics like voltage, current, and temperature at rates of up to 500,000 samples per second, and issue triggers on a scale of 1/1,000,000th of a second. This is 100,000 times faster than the blink of an eye. Field Programmable Gate Arrays, or FPGAs, allow us to process many bits of data in parallel and reconfigure our hardware to suit the needs of our ever-evolving experiments. With that, let me show you into our control room, the heart of our fusion endeavor. All of the data that I previously mentioned is visualized here, giving our operators the key information they need to perform fusion experiments. On a given day, about a dozen people populate this room, each with a unique role to play. Together, they execute between 50 and 60 shots per day, with each shot generating over 10 gigabytes of data.
from around 7,000 diagnostic channels. We've catalyzed around 70,000 shots inside this machine, putting our total data usage at nearly a petabyte of storage. For context, that could fill a 256 gigabyte drive almost 4,000 times over. Many of these shots also utilize the power of machine learning. Through our long-term partnership with Google, we have been able to combine the vast expertise of our team with the optometrist algorithm to improve our experimental outcomes using Monte Carlo optimization. This is just one of many of the collaborations we have fostered with other organizations in the pursuit of limitless clean energy. And with that, this concludes our tour. Thanks for joining us on this journey today. It's been a pleasure to give you a glimpse into what our world will look like in the not-so-distant future.